Namaste, Namaste everyone. Welcome to second PUC physics class. We were in AC circuit and we have studied how does current vary. Namaste, hope you are doing well. Welcome to the class. We have studied in the previous class how does current and voltage vary in a purely resistive circuit. We know that current and voltages in a purely resistive circuit are in phase. Whereas in a purely capacitive circuit, if you take a capacitor and connect it to an AC source, in the beginning current will be leading and it will be at the highest value, and as the time passes current decreases and voltage increases. Means current leads the voltage by an angle of pi by 2. We will revise it and then we will move on to another circuit, that is inductive. We have studied in the previous chapters three important components. One is resistor, which opposes the flow of charges because of the collision of electrons, a capacitor containing two metal plates which stores the energy and charges, and an inductor, a simple coil. Because of the change in the magnetic field through it, it induces an EMF in itself. So we have seen all the three components. Now two components, their behavior and how does current vary with the voltage in an AC circuit, in a resistor and capacitor, we have seen the two components. The third one, inductor, we have to see that. Before going to that, we will revise what has happened in a resistor and in a capacitor. And you know that in a resistor, it is very simple. We will start from here. Hope you can see this. Right. Today I made the camera to see the full view of the board. So we will take an AC source and connect it to a pure resistor and a wire of resistance R. Let V is equal to Vm sin omega t be the applied voltage. Hope you can see this, whether this is visible or not. Yeah, this is visible. Yeah, this is okay. Right. V is equal to Vm sin omega t be the applied voltage. And you know that if you want to get current, I is equal to V by R, simply the Ohm's law. And what does this give? I is equal to V by R. V is Vm sin omega t by R. By R. Of course, take a paper and start writing this. You bring a piece of paper or any book, scribble it as I write it. This is most important one, and if you don't revise this, it is of no use. So better you take a paper and write it as I write it. This is just scribbling, right? Hope you have that. Otherwise, pause the video, get a paper, get a pen and start writing it. Right. So what is the current? I is equal to V by R. V is alternating voltage. It is not a constant voltage, steady voltage. It is varying current, varying voltage, and variation is given by sinusoidal equation by Vm sin omega t. Now what is Vm by R? Vm by R can be taken as the peak value of Vm by R can be taken as the peak value of current, because when the voltage in the resistor is highest, current should be highest because it should obey that Ohm's law. And so what is I is equal to Im sin omega t. So this equation 2 compared to the first equation, V is equal to Vm sin omega t. These two equations say that in a purely resistive circuit, current and voltages are in phase because there is no phase difference found in the two equations. Both are representing sin omega t. That means when voltage is highest, current is also highest. When voltage reaches to 0, current also reaches to 0. When voltage reaches minus maximum, current reaches minus maximum, and so on. How do you represent it in a phasor diagram and a vector diagram? This is so phasor diagram and a wave diagram. This is for phasor and this is for wave. And for wave diagram, if you choose voltage like this, then current will also be following the same fashion like this. And when voltage is highest, current is also highest. Voltage is 0, current is 0. This is the phase angle omega t at any instant, and this is V or I. We are choosing the same axis for two quantities, voltage and current. I think better I write V and I both. Okay. Okay. And now break this circuit or find out what happens at a particular instant of time like this, that is omega t1. At that instant omega t1, here will be the that is current, and this will be the voltage. Okay, and shall I represent it properly? Hope you are following this and you are doing the same thing, right? As I do. This is V. Oh, it shouldn't reach such a high value. Okay, it should reach like this. This should go up and like this. Okay, this is V, this is I, and this is omega t. Okay, now they are in phase here. In phase in the sense when current is at its highest position, voltage also should be at its highest position. They shouldn't be at different positions. The vectors will be moving together like this, and anti-clockwise direction is taken as positive now here. That is angle. That angle you can, so this is I don't have space, it has become very less. This angle is omega t1. That's how we represent it. Hope you can see that, right? Little, you can zoom it and you can see it. Yes. Now, so this is how voltage and current vary in a purely resistive AC circuit. When voltage keeps on increasing, current also starts increasing. When voltage reaches maximum, current also reaches maximum. When voltage reaches zero, current also reaches zero. Okay, negative maximum together, positive maximum together, like that. Okay, now you take a purely capacitive circuit. Connect a capacitor across an AC source. This is what we have seen in the last class. Yes, take a capacitor, connect it to an AC source of alternating EMF. V is equal to Vm sin omega t. This is the voltage that we have applied, and this is the capacitance of the capacitor. And you know that in this circuit, as the AC varies, current doesn't vary in the same fashion. In fashion in the sense, in the same instant, the fashion is different. When the voltage reaches highest, current is zero. When voltage reaches zero, current is minus maximum. Voltage follows current. Current leads. That means you should get an equation for current as I is equal to Im sin omega t plus pi by 2. It leads by 90 degrees. Like two pendulums, as I was giving the same example. When one pendulum is here, another one is here. When this reaches here, it reaches here. So one is following the other. So how did we get that? We know that charge stored in the capacitor at any instant is C into voltage at that instant. Voltage across the capacitor at any instant keeps on varying because we have applied a alternating voltage. It is not a fixed voltage. Suppose you had connected a fixed battery across the capacitor, the capacitor voltage would have been the voltage of the battery itself, theoretically. It might have reached the maximum value. But it is not so here now because the applied voltage itself keeps on changing. So what is the voltage charge stored in the capacitor? Capacitance of the capacitor, which is a constant, into V, Vm sin omega t. What is the current in the circuit then? Current is dq by dt. That means d by dt of that C Vm sin omega t. Okay. Now I is equal to, when you differentiate this, take the constants out. C Vm, they don't vary. Sin omega t, cos omega t into omega. What is I? I is equal to C Vm omega, cos omega t can be written as sin omega t plus pi by 2. So what is I is equal to? If you want to get the same equation as here, Vm by R, can you see that here? Voltage by resistance gives the peak value of current. That is what we have written. These two are changed as Im. Similarly, if you want to have such a situation here, Vm by 1 by omega c, because Vm by omega c cannot be changed, or Vm into omega c cannot be written as Vm by omega c, Vm by 1 by omega c. So 1 by x comes to the numerator. Vm by 1 by omega c sin omega t plus pi by 2. Okay, I is equal to Vm by, so how did we treat this? 1 by omega c is treated as, omega is angular frequency of AC, the angular velocity with which it turns. 1 by omega c is treated as xc sin omega t plus pi by 2. Now this voltage divided by reactance, xc is called reactance of the capacitor, so that can be treated as the peak value as if we have voltage by resistance of the resistor. Here it is not a resistor, it is a capacitor. So Vm by xc is called the Im, that is the peak value of current, Im sine omega t plus pi by 2. This is equation 2. So equations 1 and 2, if you compare these two, you will find that current leads the voltage by 90 degrees. Here you have omega t plus 0. Here you have omega t plus pi by 2. Current leads the voltage by pi by 2. You know the meaning of that. In the beginning itself, current is highest. Then the voltage rises to highest. By that time, current reaches 0. Then when the voltage reaches 0, current goes to minus maximum. So in this way, current leads the voltage and voltage follows. So these two equations. Now, when you wrote Im is equal to Vm by Xc, we have got some answers here. Im is equal to Vm by Xc, or what is Xc? Xc is equal to Vm by Im, peak value of voltage by peak value of current. That is called the reactance of the capacitor, and this is also called Vrms by Irms. If you divide by root 2, divide by root 2 on both numerator and denominator, you will get Vrms by Irms. So reactance of a capacitor is the opposition offered by the capacitor to the flow of AC, and it is the ratio of peak value of current to the peak value of voltage to the peak value of current, and RMS value of voltage to the RMS value of current, or it is also equal to, what did we get? It is 1 by omega c, that is replaced here, right? 1 by omega c. So reactance of a capacitor is a frequency dependent factor. Resistance of a resistor, resistance of a metal is not a frequency dependent factor. It is independent of frequency. Wherever you connect a 100 ohm resistor, whether you connect it to a 0 frequency DC source, whether you connect it to a 50 hertz AC source, whether you connect it to a 100 volt peak to peak value AC source, wherever it is, its resistance is 100 ohm. Because resistance of a resistor depends only on its dimensions, its material, temperature, that's all. It doesn't depend on the source. But here you see a surprising factor. Capacitor also offers resistance. We call it as reactance. It offers resistance to the flow of AC, and that resistance is not a constant. It is a factor which depends on frequency of AC. What do you mean by frequency of AC? The number of cycles repeated in 1 second, the number of times that coil rotates in the AC generator per second, number of AC cycles repeated in 1 second. That frequency controls the reactance. That means for low frequencies, capacitive reactance is highest. When nu is low, Xc is highest. When nu is high, very very high frequency, say a armature coil in a generator is rotating 50,000 per second, or 50,000 rotations per second, or 70,000 rotations per second, 1 lakh rotations per second, very high frequency. In such a case, Xc is very low, frequency is very low. Now, if you draw a graph, this one I didn't discuss it in the last class. If you draw a graph of reactance versus frequency, how will be the graph? Reactance of a capacitor, Xc, versus frequency. You know that Xc is inversely proportional to frequency. You know how will be the inversely proportional graphs always? Volume is inversely proportional to pressure, that is Boyle's law. How will be the volume versus pressure graph? It is potential is inversely proportional to the distance, V equal 1 by 4 pi epsilon naught Q by R. How is the graph? It's a rectangular hyperbola like this, right? So Xc is inversely proportional to frequency. More and more the frequency, lesser and lesser will be the capacitive reactance. Of course, I crowded everything here, so because I want space for inductive reactance. Yeah. Now that I think I can rub this. This also I'll try it once again. This is the voltage equation, right? Okay. I is equal to, we got it as Vm by 1 by omega c sine omega t, cos omega t, okay, sine omega t plus pi by 2, and we have got it as I is equal to Vm by Xc sine omega t plus pi by 2. We got this because we want to compare this equation in the later stage. I is equal to Im sine omega t plus pi by 2. This is what did we get in the last case. Okay. Now I want, this is XC formula. XC is equal to 1 by omega C, that is 1 by 2 pi nu C, and that is equal to Vm by Im, that is also equal to Vrms by Irms, because you can divide it and numerator and denominator by root 2. And any graph of XC versus frequency will be like this. It doesn't become 0. It doesn't touch even X and Y axis, because if Xc is inversely proportional to frequency, if Xc has to become 0, nu has to become infinity. So it doesn't touch. Okay, how will be the that graph? Okay, we will take this voltage varies sinusoidally like this. What about current? Current varies when the voltage is 0, current is highest. When voltage reaches highest, current is 0, minus highest, 0, something like this. So it starts like this, like this, like this. So this is I, leading, voltage lagging. Hope you have understood now, right? Current leading means in the beginning itself it is highest, voltage is 0. This is 0, minus, so like this. Okay, now cut it at an instant, at any instant. I will cut it at this instant, like this, and find out where are the phasors. That means vectors which represent current and voltages. Yes, 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 here it is like this, and here it is like this. Oh, it's going down. Okay, it is cutting here. So if this is current here leading, because anti-clockwise direction is taken as positive direction, if this is leading, okay, I, then voltage will be lagging here, because this is the position voltage, and this is omega T1, and this is actually that omega T1 position. This is not needed actually. This drop is not needed. This is needed. And so this angle is 90 degree, right? This is pi by 2. Yeah, this angle. So current leads the voltage by 90 degrees. And this is the usual phase, the phase angle at which the coil is. So in a purely, better I keep quiet. Yeah. So in a purely capacitive circuit, current leads the voltage by pi by 2. And the equations for current and voltages are: voltage is V equal to Vm sin omega t as usual, I is equal to Im sin omega t plus pi by 2, and capacitor offers a reactance X equal to 1 by omega c. Now we will take an inductor which stores energy in the magnetic field, because any change in the current through a coil induces an EMF in it, because change in the current produces a varying magnetic flux, and that induces an EMF in itself, and that property of the coil is called self-induction, and the ability to induce EMF is called self-inductance. Now connect a coil having a self-inductance L to an AC circuit. So let us take an AC source, connect it to an inductor of self-inductance L. Okay, right, you connect it to an inductor of self-inductance L S, like this. Applied EMF is V is equal to Vm sin omega t. You just recall what you have done in the previous cases, right? For current in the resistor, we have divided simply to resistance, V by R. Vm sin omega t by R, Vm by R is taken as Im. For current in a capacitor circuit, we know that charge Q is equal to CV. Once you get charge, you can differentiate it, because current through any current through any circuit is the rate of flow of charges, dq by dt. So once you get Q is equal to CV, because V is Vm sin omega t. It is a timely varying voltage. Now here, you know that when a varying voltage or varying current is applied across, alternating current is applied across an inductor coil, Okay, it induces an EMF, and you know that induced EMF is equal to minus L di by dt. Actually, all these things can be derived using that Kirchhoff's law. What does Kirchhoff's law say? Kirchhoff's voltage law. Algebraic sum of potential drops across various parts of the mesh is 0. So here, for example, you see V is the applied voltage, IR is the voltage drop, right? V plus IR is equal to 0. Similarly here, voltage across applied voltage and voltage across a capacitor is 0. Sorry, applied voltage plus voltage across a capacitor is 0. That is, algebraic sum of the potential drops across various components in the closed mesh is 0. Similarly, we will apply KVL, Kirchhoff's voltage law, loop rule. If you apply loop rule, you know that here we apply V. This is the source, AC source, which gives the alternating EMF V plus, what about the EMF induced? E will be equal to 0. That's what we can do, right? The voltage applied and the induced EMF. These are the only voltage drops that you have in this closed loop, because you have a battery, AC source, and coil which induces EMF in itself because of the change in the magnetic flux. We have only two components. One is source, AC source, another is inductor, and inductor induces an EMF in itself, and that is given by minus L di by dt, and in fact it is minus is from Lenz's law, and other things are from Faraday's law. You know that V plus E must be equal to 0, this plus this, and here is the induced EMF because of the change in the flux. Now what is E? Substituted. E is equal to, or V minus L di by dt is equal to 0. Am I right? V is equal to L di by dt. Hope you are following, right? So applied voltage and induced EMF, their sum must be equal to 0. Algebraic sum of the potential drops. V, but E is minus L di by dt equal to 0. V, bring this to the right hand side, L di by dt. Now did you get current here? But if you want to get current here, you have to integrate this one. Already it is differentiated. You have to get the integration. Now what is V equal to? Shall I rub this little bit? Yeah. V is Vm sin omega t, and I will bring L here, is equal to di by dt. Hope you have followed the steps. Right? I'll bring L here and expand V. V is not a constant voltage, it is an alternating voltage. So Vm sin omega t and L here by L is equal to di by dt. So how to get I now? You have to integrate this, but before integration I'll write di is equal to Vm by L sin omega t dt. Right? You have to integrate this term. So I'll write it here, di is equal to Vm by L, okay, sin omega t dt. Vm by L sin omega t, yes, dt. Right. Now integrate this. Let the current increase from 0 to I and let the time vary, right? Okay, we can integrate in general terms. Di, integration of di is equal to integration of Vm by L sin omega t dt. Okay, what is the integration of 1 di? That is I. Of course, here you have 1, right? 1 into di. It is same as writing di. Integration of 1 with respect to di is I, is equal to Vm by L is a constant, right? What is the integration of sin omega t? Integration of sin omega t is minus cos omega t by omega. That is how we write. Integration of cos omega t is, sin omega t is minus cos omega t by omega. Why did I put this bracket? Not needed. For example, if you integrate this, see what is the differential, if you differentiate this, you will get this back, right? I am explaining this because I think you don't have very good hold on integration and differentiation. Once you start integration differentiation in mathematics, these things are very easy. But now for the time being, see, differentiate I, it is di, correct? What about differentiate this? Vm by L is a constant. Differentiate this d by dt of minus cos omega t by omega. Will you get sin omega t? Yes. How? D by dt of minus cos omega t by omega. 1 by omega is a constant. d by dt of minus cos omega t. Minus I will take it here. This minus and omega I will take it outside. d by dt of cos omega t minus sin omega t into omega, because you have to differentiate omega t also. Minus sin omega t into omega. This omega got cancelled. Minus minus plus sin omega t. We have got it. So integration of sin omega t is minus cos omega t by omega. Now what is I is equal to? I is equal to Vm by omega L into minus sin cos omega t can be written as sin omega t minus pi by 2. This is how we can write. So minus cos theta is sin theta minus 90. So sin omega t minus pi by 2. Now you see here, we have peak value of voltage divided by some term. Last time in the capacitor, we struggled to get something here. It was together, Vm into omega c, something like that. It was here. We brought it downwards and took it as the capacitive reactance. Now, an inductor is a best coil. It shouldn't have any resistance. But when an inductive best coil is connected to an AC, it opposes the flow of AC through it. Opposition offered by an inductor coil to the flow of AC through it is called reactance of the capacitor. Reactance of the inductor, it is represented by XL. So shall I represent this as XL? I is equal to Vm by XL, that is reactance offered by the inductor to the flow of AC, sin omega t minus pi by 2. And you know what is this? Peak value of voltage divided by reactance. What may be the answer? Peak value of voltage divided by resistance, that is peak value of current. I is equal to Im sin omega t minus pi by 2. This is the equation for current. This is the equation for voltage. Compare them. What you will get? The two equations say that current lags behind the voltage minus pi by 2. What do you mean by current lagging behind the voltage? If you have a pure coil without any resistance, it should be made up of a best material which has no resistance at all. Connect that pure coil across an AC source. Just to switch it on, you find that voltage across the coil is highest in the beginning, and then voltage decreases, current reaches highest. Voltage leads, current lags. So already we have taken an equation for voltage, V is equal to Vm sin omega t. How do we say that the voltage is leading? Show that current is lagging. That is the easiest way. I is equal to Im sin omega t minus pi by 2. So because minus cos omega t, it can be written as sin omega t minus pi by 2. So this equation shows that in a purely inductive circuit, voltage leads, current lags. And they have a phase difference of pi by 2. Now we have to represent all these things in a phasor diagram. Where do we do that? Shall I rub all these things? Of course, I will deal with this derivation again in the next class. Once just a touch on that. But you should have an idea about this one. That Vm by L sin omega t dt, and you have to integrate di. Differentiation of I is di. Integration of di is I. So 1 di. That is integration is I. What about this Vm by L constant? Sin omega t integration minus cos omega t by omega. So if this term is differentiated, you will get back sin omega t, right? Minus cos omega t by omega by omega L, and omega L, this term we have to explain now. What is omega L? Shall I rub this? Okay. Omega L is the reactance of the inductor, and that is 2 pi nu L. Right? Now how did you get this omega L? Omega L is obtained it is taken as XL, and Vm by XL is taken as Im. You see this term, peak value of voltage by the reactance of the inductor, which is this one, XL. XL is taken as omega L. That is taken as peak value of current. So what is XL? Bring this XL here, Vm by Im. Sir, I want to know the reactance of an inductor. What should I do, sir? Take a coil, connect an AC source across it, find out the peak value of voltage, peak value of current, divide them. You will get the reactance of the inductor. It is also measured in ohm. Unit is same. Okay. Sir, do you have any other value which will decide the reactance of an inductor? Of course. Divided by root 2, divided by root 2 here. You know that peak value by root 2 is RMS value. So, in reactance of an inductor is also the ratio of peak value, RMS value of voltage to the RMS value of current through it. So, inductive reactance, that is opposition offered by the inductor to the flow of AC, is also defined as the ratio of RMS value of voltage to the RMS value of current. And inductive reactance is also equal to omega L, which is equal to 2 pi nu L. Inductive reactance is directly depending on the frequency. Now, of course, when frequency is 0, inductive reactance is 0. Now, if you want to draw a graph of XL versus frequency, shall I draw it in the same graph? XL versus frequency, same frequency. How will be the graph? XL is directly proportional to frequency. Graph is like this. Any directly proportional graph is a straight line, because when nu is 0, XL is 0. When nu is more, XL is more. So it should be a straight line. Y equal to mx plus c. So this is for XL and this is for XC. So inductive reactance is the a factor which depends on frequency also. That means inductive reactance and capacitive reactance both depend on AC source across which it is connected. But resistance of a resistor does not depend on the AC source. It is always a constant, independent of the source across which it is connected. Of course, here I must have introduced one constant. After integrating this, I must have introduced a constant here. You will understand what is this constant once you study integration properly in mathematics. Because you see, suppose you have equations like this. You may be remembering, I was dealing it in some of the class in first PU. It was like this. Shall I rub this here? Just for introducing that. It is like this. For example, d by dx of 6x plus 5. What is the answer? It is equal to, differentiation of 6x is 6. But differentiation of 5 is 0, right? So 6 plus 0, that is 6. What is the d by dx of 6x plus some 10? It is also 6, because d by dx of 6x is 6 and differentiation of 10 is 0. So it is always 6. But then what about if you integrate 6? If you integrate 6, we will get 6x. Integration of 6 dx is 6x. But what about this plus 10 or plus 6? What is this? We don't know. Because while differentiating, whatever is the constant here, we got the answer after differentiating it as 0. Now while integrating, will you get that constant back? No, because differentiation of a constant is 0. So we write simply a constant. We rub this plus a constant. So whenever we integrate a term, we integrate it and write a constant. We don't know whether there was any constant before when we differentiated it. This is a constant. But we don't write that constant, we write it as 0. Why? Because this is the equation for current. Sinusoidal current, timely varying current. If it is an equation for timely varying current, it should contain a term which is a function of time. It should not contain a constant. This indicates that the current is a constant, not possible. So equation for current should be a time dependent, not time independent. You can't have a constant here, it should be 0. So we continue it like this. Of course, all these ideas of integration you will come across in mathematics, and once you get that, you will get the idea. So I is equal to Im sin omega t minus pi by 2. This, okay, we have to indicate it in a phasor diagram now. Okay, I'll rub all these things. See, and you have to know the difference between this and whatever I draw now. So a purely inductive circuit. The points go like this. I have to finish it now. Yes, this is an AC source, this is an inductor coil. Okay, V is equal to Vm sin omega t is the applied voltage, and I is equal to Im sin omega t minus pi by 2 is the result that we have obtained. Current lags behind, LAGS. Lagging behind means going back. Lags behind EMF by pi by 2. That you know. and inductor gives a reactance called inductive reactance, which is given by omega L 2 pi nu L, and it is also equal to Vm by Im Vrms by Irms. Okay, it is a frequency dependent reactance. Now if you want to draw the phasor diagram and wave diagram, yes, we will represent voltage first. Hope you can see this. Yes, now it is full board is visible. This is voltage. Okay, I'll represent it here itself. V. This is V and I both. This is omega t. Yes. How will be the current? Current should lag behind, right? Current should lag behind the voltage. Now how will you show that? If you start current from here, it is leading. It should be lagging behind. How should it be lagging behind? You can see this diagram, right? Here you see current is leading. And now if I can show it like this, yeah, I can show it like this. I will start current from here. When this is 0, this is minus maximum. When this reaches maximum, current should be 0. If current is lagging behind voltage by pi by 2, if current is lagging behind by pi by 2, when voltage is maximum, current should be 0. That is what we had last time, right? Current was leading voltage by pi by 2. What do you mean by that? When current is highest, voltage was 0. Now voltage when it is highest, current should be 0. It means it should start from here. Then when this is here and this is not the dot that I have to connect. This dot is not to be connected, and here and then here and then here. So it should be like this. You see the diagram, this is I. See, when voltage is highest, current is 0. Current is it is coming at, right, it has not reached maximum. When current reaches maximum, voltage reaches to 0. So now you can see the same diagram here. If I close it here, you can understand, right? You see, you can understand. Current is lagging. How do you say that current is lagging? When voltage is highest, white one, purple, current is 0. Current has just it has not yet started, right? So just waking up, current, and that voltage has already gone to plus maximum. When voltage reaches 0, now it wakes up and goes to the maximum. So current is lagging current. It is lagging. Okay, LA, and this is leading. Voltage is leading. Now break it at a particular instant, particular phase angle. Break it here. Yes, a particular instant here. Then find out where is phasor and where is current phasor and voltage phasor. Now it is easy because they are separated. Of course, current should be lagging behind, right? Voltage should be leading. Suppose voltage is here, V, and if this is omega T1, okay, this is omega T1, then current should be lagging behind. It should be somewhere here, right? Here, we have got it here. Yes. Then this should be here, and this should be 90. You know why it should be 90? Because voltage should lead. This is I. Hope you have followed. You see it here? Current was leading. Voltage was in the same position, you say, always, because every time we used the same equation for voltage. V is equal to Vm sin omega t. That was the reference every time, because that is the AC source we have connected. You see here, voltage is here. Can you see? Voltage is here. Here current leads. Voltage is here. Here current lags. That's all. So here current leads from the voltage, same voltage, current lags. So in a purely inductive circuit, current lags behind, voltage leads. Even the inductor offers opposition to the flow of current, and that is called inductive reactance. And inductive reactance is directly proportional to frequency of AC, whereas capacitive reactance is inversely proportional to frequency of AC. And you can remember it like this: in which circuit which lags and which leads. In a purely capacitive circuit, you know it. Where is the capacitor? Okay, we have rubbed it. In a purely capacitive circuit, current leads, right, and EMF lags. You read it yourself. In a capacitive circuit, current leads, EMF lags. Read it yourself. In a purely inductive circuit, EMF leads, current lags. You read it as you like. I don't want to pronounce this anyway. Both, you remember it as you like. In a purely capacitive, in the middle, current leads in the beginning, voltage lags. In a purely inductive circuit, in the beginning EMF leads, current lags. So it is left to you, right? How do you use this word? So these three components and their formulas, you see, you should have a list of formulas and all the ideas very clearly, because most three important derivations of this chapter are over. Now you have very, 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 very important derivation, clubbing all the three things together. Means you have to connect an inductor, capacitor and resistor, all the three together in a circuit. If you connect a resistor, capacitor and inductor, all the three components in series in a circuit, which leads, which lags, whether current leads, whether voltage leads, resistor says it says current and voltage, you must be in phase. When voltage is highest, current should be highest, no phase difference. Capacitor says current, you lead, right? You just go on increasing is your value, let the voltage increase later. But inductor says no, voltage should lead, current should lag behind. So who will be the controller in the whole circuit? If you connect capacitor, inductor and resistor in a series AC circuit and apply an AC voltage across it, it's a beautiful thing to see now. If you connect all the three together, we will see it in the next class. But before going to that, you must be very thorough with all these things. We will revise it in, so we will use some 20 minutes or so to revise all the things which you have studied in this class. Then we will go to the series circuit, that is called series resonance circuit. In the same series resonance circuit, that is the most important derivation, either problem or derivation, 100% assured in final exam. Even for entrance exam, that part is very, very important and very easy to understand also. Once you have understood all these things clearly, you will come to know what is resonance in electricity, right? Electrical resonance. That we will see in the next class. Thanks for watching my class. We will meet in the next class in the, while discussing resonance circuit. Thank you.